All right, welcome back again. I'm Amy Lumley, and this is a really short section. This is about how to calculate average atomic mass. So we're going to go over the concept, do a problem, and then I have a theoretical problem for you to think about. Enjoy. Okay, so quick review. All elements have a specific number of protons, so all atoms of that element have the same number of protons. The neutrons vary. Because the neutrons vary, that means when we add together the protons, which are always the same, plus the neutrons, which can be different or they might be the same, your mass may be the same or it may be different. Because those masses can change, we have to take that into account when we give what's called an atomic weight. This is a weighted average of masses of all of the isotopes that we have. Now, normally, this is what's given on the periodic table. You'll see it usually listed as a decimal, and these are going to be measured in U's. Okay, U stands for Unified Atomic Mass Unit. You also might see AMU, which is Atomic Mass Unit, or another term you might hear is Dalton, DAL. That's an older variation. You probably won't see that, but AMUs and U's are really quite common. Now you might wonder, what do you mean by a weighted average? So here's the example I give a lot in class. Imagine there's 10 students in class, and you're thinking, oh no, it's a word problem. Hang with me here. 10 students in class. 9 of those students are 6 foot tall. So I have 9 students that are tall. And then I have 1 student, just one, that's 5 foot tall. What's the average height? Well, average height. Now you've learned a long time ago, average. You take the numbers, you add them together, and you divide by the number of samples. So some people will say, okay, I'm going to take that 6 foot and that 5 foot, I'm going to add them together, I'm going to divide by 2. It's going to give me 5.5 feet. But that's not a true reflection of the distribution of that class. Most of the students are closer to 6 foot. So what you'd have to do is you'd have to add 6 foot plus 6 foot plus 6 foot plus 6 plus 6, 6 plus 6 plus 6 plus 6, woo, plus that 5 foot student, and then divide that answer by 10. So your answer would be closer to 6 foot than it would to 5 foot. So you have to remember to take into account the distribution or the percentages of those different isotopes. Okay, so here's one where we're going to look at the what's called the average atomic weight of an element. It says calculate the atomic weight of chlorine from a knowledge of the abundances, so it means that they're in different amounts, of its most common isotopes. The isotope of mass number 35 makes up 75.77% of all chlorine atoms, while the isotope of mass number 37 accounts for 24.23%, the remainder of chlorine atoms. All right, so the easiest way to start this one, remember, you can't just add them together and divide by 2. It doesn't work that way. If we look at the percentages, most of them are closer to that chlorine 35. So the mass is going to be closer to 35 compared to 37 because fewer of them are 37. So I would expect the mass to be 35 point something. You know that the mass will be somewhere between that 35 and 37. All right, so here we go. We're going to say that the chlorine 35 makes up 75.77%. Okay, I'm going to teach a little trick. We're going to change this back to a decimal. So from a fraction, a percent, sorry, that wasn't a fraction, a percent, back to a decimal, we divide by 100. We're going to move it over 2 decimal spots. Make sure to always move it 2 decimals, 0.7577. And we're going to multiply that by the mass. So here's the mass. Here's the percent. Change to decimal. Change. Didn't give myself enough room to write here. Change to decimal. And then we're going to multiply that together. Now, I don't have this written out. I'm actually using a calculator right now. So give me just a second to find that answer. 26.5195. Yeah, I'm just going to write down all the numbers it gives me. Then we have chlorine 37. We're going to take the percent. We're going to change it to a decimal by moving it back 2 spots. We're going to multiply that by its mass, 0.2423 times 37 gives me 8.9651. And then we are going to add these two together. So 6, 14, that's 8, that's another 14, 5, 3. Put my decimal in. Now here we're looking at the mass, average mass of one atom. So our units are going to be AMUs or just U. There we go. There's our answer. So once you add them together, that's your final answer. Now, earlier I said because the chlorine 35 isotope has a higher percentage, that the mass will be closer to 35 than it will be 37. And you can see that ends up being true for this particular example. If you look at this and say, oh, but it's not exactly like what the periodic table says, there's actually a third isotope we didn't include. But for the test, this is what you need to show me. All right, so here is your last question. This one is a tricky one. So let's read this one. Hydrogen can exist as 3 different isotopes, H1, H2, and H3. Again, they all have 1 proton, but they have different mass numbers, and that's what's making it into different isotopes. The average atomic mass listed on the periodic table is 1.008. What would be the most abundant isotope? H1, H2, H3, or all of the isotopes have equal amounts? Now, this one is kind of tricky. It makes you think. Now, there's actually no math associated with this particular problem. One thing you do have to realize is that H1 has a mass of 1, H2 has a mass of 2, and I'll let you figure out what H3 has. It has a mass of 3. And we're trying to figure out if the average is closest to 1.008, well, what's going to be the highest percentage? I'll tell you, they're not equal. Generally, those isotopes do not have equal percentages. Because this number is closest to 1, guess what? H1 is your answer. So that one, no math associated with it. You just had to be able to think it through. And that concludes this section. Come back for the next section, which is all about the periodic table and how it's not something to fear.